Good morning to you all. Thanks for coming. My name is Ashraf Aboulnaga, and I'm a professor here in the School of Computer Science. If you join Waterloo as a CS undergrad, you would probably get me teaching you operating systems in the third year or database systems in the third or fourth year. But today I won't talk about operating systems or database systems. I want to talk about something more basic, something that should give us all a flavor of the kinds of math and engineering issues that are involved in computer science. And my presentation will be about how Google works. Okay? And there are other search engines like Bing, and what I say about Google would apply for any other search engine that you use. So how does a search engine work? And we all use Google, but to kind of illustrate the kinds of questions that I want to talk about today, let me go to Google. And if I go to Google and type in computer science, if I can type today, Waterloo, it gives me a list of pages Here is the list of pages that Google thinks are relevant to this query, as we call it. And sure enough, the first page on this list is the page of the Waterloo School of Computer Science, which is a pretty good answer for this query. Now, if I go to Google and type in my name, it also gives a list of pages. And the first page on this list is indeed my home page. So, wow. Let me shrink this a little. Yeah. Okay. So how does a search engine like Google do that? And in particular, how does Google know that the page exists? How did Google know about my homepage? And when I typed my name, how did Google know that this page is relevant to the query? And finally, when it found all the pages relevant to the query, how did it decide which page should come first? So when I type computer science Waterloo, there's a ton of pages that talk about computer science and a ton of pages that talk about Waterloo. How does it know to give me the exact right page first? And I'll talk about each of these three questions in my presentation today. So the first question will require us to talk about something called web crawling. The second question will talk about web index, will require us to talk about web indexing. And the third will require us to talk about search engine ranking. So let's start with crawling. How does Google know about all the pages on the web? And the answer is that pages on the web link to each other. And Google will find all the pages on the web by following these links. So if I go back to the School of Computer Science homepage, I'll see that it has a link up here that says Our People. And if I follow that link, it has a link to my homepage. If I follow that link, I will find my homepage. Let's see. So the way this works is, or the way web crawling works is that, the way Google finds all web pages is that it starts, there is a program that starts with one page or some pages and follows all the links on this page to get to other pages. And then it goes to that other page and follows all the links and get to other pages, and so on and so on and so on. So to illustrate this further, let me go back to my home page. And let me view the source of this home page. So what I'm seeing in the browser is a home page with a picture of somebody here and a name in big letters, and then a bunch of links and other information. But behind all of that, there is some text marked up with this special markup, which we call HTML. It's a markup language. I know many of you know HTML. And this is the textual representation of my home page. So my name is here, and this markup here says that this should be the title of the home page. And this markup here says that the word Ashraf Aboulnaga should be on the home page, and it should be in big letters, a little bit smaller is associate professor. And then there's all these links. So there's this special markup that makes up the home page. And my browser, the program that I use to see the web page, understands this markup. So when it sees this image tag, it understands that it should find a file called ashrafaboulnaga.jpg, and that's an image. It should go fetch that file and show the picture in that file. Okay? One type of markup is this A tag. And A says that this is a link. So if I go back to my home page, I will see that I have some links. There's a link to the School of Computer Science. There's a link to University of Waterloo. There's a link to a page about the city of Waterloo, and so on. And if I go to the source of my home page, I see that these links are all represented by these A tags. So my browser understands how to interpret these A tags by displaying, so I have a link to the Cheriton School of Computer Science, so my browser understands that it should display the words Cheriton School of Computer Science and underline them, and if I click on this link, it would take me to this other page. Now, when Google wants to find all web pages, it writes a program that understands these links. But instead of displaying them on a page, it would actually follow the link to go to that other page. So you have a program, just like your browser goes to a web page and gets it on your local computer and displays it on the screen. Google has a program that goes to a web page, gets that web page, and then looks for all the links on the web page. And instead of displaying them on a screen, it actually follows them. So the program can start from here and follow the link here to here to here to here, and then also start here again and follow the links here to here to here to here. And eventually, the program will find all pages that are linked to each other on the web. What if there's a page that's not linked by any other page? And that page won't be found by Google. That page will not be part of the Google index. So this is the basic idea of web crawling. Going for this program that goes from page to page is called, as we refer to it as the web crawler. And the issue with web crawling is that the web doesn't look like this. The web looks more like this. The web has billions upon billions of pages. Google doesn't disclose how many pages it indexes, but people estimate it to be around 8 billion. So there is a lot of engineering that goes on to crawling and indexing 8 pages. So you don't just have one program on one computer going to our web pages. You have thousands upon thousands of computers owned and operated by Google that are crawling the web. So these web crawlers get a list of pages that you just know exist. So I just know that cs.waterloo.ca exists, so I start crawling from there. And from there I can find all of the pages that are linked to by cs.waterloo.ca. I can go to, for example, cbc.ca, and I can find all of the pages linked to by cbc.ca. And this is not done by one computer, and whenever a crawler visits a page, it sends it back to Google. There's thousands of these programs executing at the same time on thousands of machines, and they're all sending the pages they find back to Google. So there is an engineering issue. Basically, it's a big engineering problem. How do I write a distributed web crawler, as we'd call it, that consists of thousands of different programs that are all crawling at the same time and sending their data back to Google? Distributed means that it's different computers in different places working on the same problem at the same time. And just to give you an idea of the kinds of engineering issues involved, let me go back to Google and type in Google data centers. And I find a nice page about Google data centers. And on this page, there's a bunch of images, a bunch of pictures about these data centers that Google uses. So let me start with a picture of the building itself. Here's one. So Google has several of these. Oh, this one is not showing well. Let me find another one. So if you look at this picture here, you'll see this massive building, this warehouse. It's basically a huge warehouse full of as you see here, rows upon rows of computers. So rows upon rows of computers, and they're all part of the infrastructure that Google uses to support its search. And as you can imagine, operating such an infrastructure is a lot of engineering efforts. Writing the programs that run this infrastructure is not straightforward. And the main problem comes from the fact that you're operating at a very large scale. You're dealing with billions upon billions of web pages. But the basic idea is still the same. Follow the links from page to page. Every time you find a new page, send it back to Google. So this is the first question. How did Google find the different web pages? How did Google find my web page? It found my web page by starting from the computer science web page and then following links until it found my web page. Now, the next question is, how does Google find a page that's relevant to a query? So when I typed computer science Waterloo, how did Google know to give me the page at cs.waterloo.ca? And the answer is that you need an index for the web. So just like in a textbook, in the back, you have an index that tells you for every word, here are the pages on which this word occurs. You also need, or Google needs, an index of the web that has a list of all the words in the English language, but not just in the English language, a list of all the words in all the languages, including proper nouns, common nouns, misspelled words. And for each word, you store a list of pages on which this word occurs. So the word computer occurs on, I would assume, millions and millions of pages, and one of them is cs.waterloo.ca. The word science also appears on millions of pages, and one of them is cs.waterloo.ca. The word Waterloo appears on maybe thousands of pages. One of them is cs.waterloo.ca. So when I type computer science Waterloo, Google goes to this index, and it finds all the pages that have the word computer, and all the pages that have the word science, and all the pages that have the word Waterloo, and does an intersection among these three sets, and says, oh, okay, so cs.waterloo.ca is one of the pages that has these three words. So cs.waterloo.ca is one of the pages that are relevant to this query. There may be other pages, but basically this is the idea, that you do an intersection of, for each word in the query, you find all the pages that contain this word, and then you do an intersection of the sets. So I find all the pages that talk about computer science and Waterloo. But the next question is how to rank the pages. And before we go to that, remember that we're dealing with 8 billion pages here. So this index is massive, and you can't store it on one computer. You can't process the millions of queries that Google gets a day on one computer, so you have to do it on many, many computers in parallel, which is, again, an engineering challenge. So we found all the web pages that refer to computer science or that talk about computer science in Waterloo. Which one should we show first? And this is the question of how to rank the web pages, web page ranking. So I showed you 2 pages, and both of them have the words Computer Science Waterloo. So the School of Computer Science web page has the words computer science, and somewhere here there's going to be University of Waterloo up there. And my home page also has the words computer science. Yeah, computer science Waterloo. So which of these 2 pages is a better page to put first for the query computer science Waterloo? I guess all of us would agree that the one on the left is more relevant. If I'm asking about computer science Waterloo, I don't want to get back the home page of some person. I want to get back the home page of the School of Computer Science in Waterloo. And as we saw, Google knows how to do that. So the question is, how does Google know how to do that? And the answer is that it depends on the links. The links tell us which pages are important. So let me ask you a question. If I look at this red page here, so this diagram here is a representation of a set of web pages linking to each other. So every rectangle is a web page, and every arrow is a link from one page to the other. So if you look at this diagram and look at the red page and the green page, which of these 2 is important? Is red more important or green more important? How many people say red is more important? How many people say green is more important? So of the people who say red is more important, why did you say that? Can somebody volunteer to say why is red more important? Yes? Yes, so red is more important because there's more links pointing to it. There's more pages think that this red page is worth linking to. So more people thought that red is more important than green, and in this case, the majority wins. Yes, red is indeed more important than green because many other pages link to it. So this is the first component of ranking, that a page that many people link to is an important page. So if we look at blue and green, how many people think that the blue page is more important? Okay, how many people think the green page is more important? Nobody. So everybody agrees that the blue page is more important. Why? Why is blue more important than green? Yes? It's being linked to by the red page, which is important. So a page linked to by an important page is important. So you can think of these links as votes. And if a lot of people are voting for your page, if a lot of people are linking for you, if a lot of people are saying, like I am saying on my home page, if you want information about computer science in Waterloo, go here. So from my home page, I'm linking to the School of Computer Science in Waterloo homepage. And many other people are linking to that homepage. Everybody who links to the CS homepage gives a vote to that homepage. So that raises the importance of the homepage. Now, if there's an important page, and that important page votes for me, then I become important. Okay, so basically it's a matter, it's the basic idea is that when a page links to another page, then the page that's doing the linking is voting for the page that's linked to. And the more pages voting for you, the more important you become. And when an important page votes for you, you also become important. So this gives rise to this algorithm called PageRank. And PageRank is the basis of the ranking done by Google. It's interesting because it's an algorithm that ranks pages, but it's also an algorithm that was developed by somebody called Page. So the founders of Google are Larry Page and Sergey Brin, and they developed this algorithm, so they called it PageRank after one of them. So the PageRank algorithm is relatively simple to explain. So every page starts with an equal weight. So before I start, so first of all, what's the input to this PageRank algorithm? The input to this PageRank algorithm is the set of web pages and the set of links from one page to the other. So the algorithm knows about the set of pages and the links from one page to another. And initially, the algorithm doesn't know which page is more important than the other. So all pages are given equal weight. So let's say that we represent importance by a number, and the higher the number, the more important you are. So everybody in the beginning gets an importance of 1. So this importance, we call it the rank. So every page starts with an equal rank. Let's say every page starts with a rank of 1. And then this algorithm goes through a step that it does over and over and over again. So the step is that you add the rank of a page to every page that it points to or links to. So if you look at this red page here, initially it had a rank of 1. But then the first time the algorithm works, it will take the rank of this page and this page and this page and this page and this page, which is 1, 2, 3, 4, 5, and add them all to the rank of the red page, because they all point to the red page. So immediately the rank of the red page goes from 1 to 6. Now what about this green page, which we agreed is not important? Its rank will not change. Nobody's pointing to it. It will give its vote to other pages, but nobody's voting for it. Okay, so now in the first step of the algorithm, the red page became more important. Now, in the second step of the algorithm, the algorithm will do the same thing again. So it will look at the importance of all of the pages or the rank of all of the pages, and add the rank of every page to every other page it points to. So the rank of the red page, which is 5, will be added to the blue page. So the blue page will get a boost in importance. And this continues until the relative importance of the pages does not change. So after the first step, I'll discover that the red page is important because lots of other pages are pointing to it. And then the second step, I'll discover that, the blue page is also important because there's one important page pointing to it. And this will continue until I find out which are the important pages and which are not the important pages. So when I get a query like computer science Waterloo, I can look at the index and find all of the pages that talk about computer science Waterloo. And then I can use this algorithm to figure out which are the more important pages, and it happens that the most important page is the School of Computer Science in Waterloo homepage. Okay? Now, I talked a bit about the kinds of engineering issues that come up when designing a big distributed system or a big search engine like Google, but there's also math and algorithmic issues. By the way, I use the word algorithm. What's an algorithm? Algorithm is a sequence of steps that a computer can follow to accomplish a task. Right? So I can't just tell a computer to tell me what's the most important page. There has to be a sequence of well-defined steps. And you would represent these steps in a computer program in some programming language like Java or C or Python or whatnot. So I can take these steps and write them up as a computer program, and the computer will follow the steps described in this program. So this sequence of steps is what we call an algorithm. And in computer science, a lot of what we do is about developing algorithms for different tasks. So this is the math side of computer science. And in this case, what we're seeing is an algorithm that deals with a mathematical structure known as a graph. So graphs come up a lot in computer science, and I want to spend the rest of my talk discussing graphs. So what's a graph? A graph is a mathematical object or a mathematical representation of a set of objects where some of these objects are connected by links. So for example, if every rectangle here is a web page and every arrow is a link from one page to another, then the objects in this, then this is a graph where the objects are web pages, and there's a link between two web pages if one points to another. There's many other contexts in which graphs arise. So this could be a graph where each object represents a city, and there's a link between two cities if there's a highway between the cities. On Facebook, you can have a graph where every object represents a person or a Facebook account, and a link exists between two accounts if one is a friend of the other. So if this is a Facebook graph, then 4 is a friend of 5, 4 is a friend of 3, 4 is a friend of 6. And when we talk about graphs, we usually refer to the objects as vertices. So every object is a vertex, and the set of objects is the vertices. And these links, we call them edges. And the links can have a direction, or they might not have a direction. So in the web, these links do have a direction. So if I link to the School of Computer Science homepage, this is a link from me to that page. There's no link in the other direction. But if I talk about cities and highways, for example, if I have a highway connecting two cities, I can go out this highway in either direction. So on the web, if I'm talking about web links, there needs to be an arrow on each edge indicating from where, with the direction of this edge. But if I'm talking about something like a highway network, then there does need to be an arrow because an edge goes both ways. Or if I talk about Facebook friends, if 4 is a friend of 5, then 5 is also a friend of 4. There doesn't have to be an arrow because there isn't really a direction for this link. So in this case, we call this an undirected graph. And there's lots of interesting questions you can ask about graphs, lots of interesting applications in which you have graphs. So we just saw one, which is if you represent the pages on the web as a graph, you can do some analysis on this graph or run an algorithm on this graph to figure out which pages are more important than others. In the context of the web, you can think of the internet itself as a graph where every vertex is a computer and every edge is a link between computers. So the internet is a computer network. It consists of computers connected to each other, so you can have you can have a graph representing the connectivity of the computers on the internet to each other. So lots of interesting questions about graphs, and lots of interesting things you can do with graphs. And to give you a kind of a general idea of the kinds of questions and the kinds of thinking that you have to do when you talk about graphs, I have this activity for you. So if you bring up the activity where the first page has a graph that looks like this, and what I want you to do is, starting with this vertex labeled start, find the minimum number of edges, or mark the minimum number of edges required to connect all the vertices. So going back to my web crawling example, if this is a graph representing web pages, every circle here is a web page, and every arrow, every edge is a link from one page to another. I'm going to start at this page, and I want to visit all of the pages. So I can start from here and visit this page. And then from the same starting point, I can visit another page. And then I notice there's a link from this page on the top to this page here, so maybe I should follow that link and visit the page. Now, did following this last link add any new information to me? Did it allow me to find a new page that I didn't know about before? No. I'd already seen both of these pages, so why go from one to another? So this is the idea of the minimum number of edges. How can I visit all of these vertices while following the minimum number of edges? So I would not follow this edge. Maybe if I'm here, I'd go visit some other vertex, maybe when I visit some other vertex, and in the end, I want to visit all of these vertices while following the minimum number of edges. From one vertex, I can visit as many of its neighbors as I want, but I don't want to visit a vertex. I don't want to follow more edges than you need to. So I'll let you work on this activity. Take maybe 5 minutes to do it, and then we'll come back and see what's a good solution. One more thing I want you to do. When you're done, count how many edges you got, how you had to use. Okay, so let's get back and see what people did. So here's one possible solution. Here's the solution I came up with. I said that I'd go from the start vertex and then visit 1, 2, 3, and then from here visit this one, from here visit this one, from here I want to go all the way up to here. And then the end, I used 14 edges. So how many people were able to do it in less than 14 edges? So this is 14 edges. And by the way, this, if you look at what I have in blue here, this is also a graph. It consists of vertices connected by edges. And this particular graph is called a minimum spanning tree. So a tree is a special type of graph where the edges branch out but never branch in. So if I look at the slide from the side, I see that if I can see that it looks kind of like a tree. If I start from here, this is the root of the tree, and then it branches out, and sometimes you have branches that branch out even more, but you never branch in again. I never have two branches that connect to each other and branch in again. I can always branch out, but I never branch in. A graph that follows this structure is called a tree. And we use trees all over the place in computer science. If you study computer science in university, I bet you that the first computer science course you talk about, the first computer science course you study will have something about trees. And this particular tree is called the minimum spanning tree. It's a spanning tree because it covers all of the vertices of the original graph. It's minimum because it has the smallest number of edges. So the question is, here I used 14 edges, and I had 15 vertices. So my graph has 15 vertices. Is 14 edges a good number to use for 15 vertices? Can I do any better? So I hear a lot of no's. And you're right, you can't do any better than 14. So can somebody explain to me why you can't do better than 14 edges? So the gentleman up there.
N minus 1. So if you have 15 vertices and for each edge we connect two pairs, and so 14 would be like the minimal amount of edges that you can have to find the answer.
So what would happen if I remove one of these 14 edges?
One of the 14 edges, like 13?
Yeah, I mean, would I still have a minimum spanning tree if I remove one of these 14 edges?
No, right?
No.
No.
Because I would, then there would be a vertex that's not connected. Yeah. So I have 15 vertices, and I want to connect all of these 15 vertices with my tree. So every vertex has to have at least one edge going into that vertex. Okay, and then I have the vertex I'm starting from, which doesn't need an edge going into it. So I'm starting from one vertex, and I want to go into 14 other vertices. So that I need 14 edges to go into these other vertices. I can't do any better. So we can show, so this notion of you can't do any better is a notion that Professor Monroe talked about in his lecture, which is the notion of optimality. So 14 vertices is optimal. It's the best you can do. And as we saw, I can actually prove it. And this is something we do a lot in computer science. When we study a problem, we don't just want to come up with an algorithm for the problem, we also want to know, is this a good algorithm or a bad algorithm? We have to have a notion of goodness or badness. So in this case, the notion of goodness is you use as few, if you use fewer edges, you're better. And we can also find, we can sometimes prove that this is the best you can do. This is optimal. So if you find a minimum spanning tree that has 14 edges, don't bother looking for one that has fewer edges, because this is the best you can do. Okay, and a related issue is to show that some problems are really hard. The best you can do is still very complex. But as I mentioned, one of the things we do in computer science is study whether problems are hard or easy, and study for a particular solution to a problem if this is a good solution or a bad solution, if this is the best you can do, or if you can do any better. So for a minimum for a graph that has n vertices, n minus 1 is the best you can do. N minus 1 edges is the best you can do for the minimum spanning tree. So let's make things a little bit more interesting. Let's add weights on the graph. So if you go to the next page in your activity, you'll see that this is the same graph, but now I've added numbers on the graph, on the edges. And these numbers represent weights for the edges. So for example, if this were a road network where every vertex is a city and an edge is a highway connecting two cities, then these numbers might be the distances of the highways. Going back to our web crawling example, these numbers might represent the speed of the link. So, or the time it takes to traverse a link. So a larger number means that it takes more time to traverse a link, so it's a slower link. And in many cases, you have these weighted graphs, which are graphs that have weights on the different edges. These weights represent costs of traversing the edges. The distance you travel on the highway, or the distance you travel by plane, or the speed of a computer link, of a link between two computers. And in many cases, we want to find the minimum cost route, or the minimum cost spanning tree, or the minimum cost something or the other. So in this case, if I give you this graph, and I give you these weights on the different edges, what I want you to do is, again, find the minimum spanning tree, but I want you to find the minimum spanning tree that has the lowest possible cost. So if your tree will have a number of vertices, your tree will have a number of edges. If you take the sum of the weights on all these edges, I want it to be as small as possible. Okay? So take 5 minutes, and we'll come back and see if we have a good solution or not. Yes? Okay, so how are you doing here? So has anybody added up the cost of their minimum spanning tree? What's the minimum cost spanning tree that you got? Somebody shout out the number you got. Yes? 365. That's really good. Somebody 348. 345. Okay, so let's see. So I came up with this minimum spanning tree. Okay? So if you notice, what I have here is, it's still a tree. If I look at it from here, I see that it starts at the root and then it branches out, it branches. Here I have funny branches going back, but still, the main property of a tree is that once the edges branch out, they never branch in again. And the total cost of this tree is 366. So I'm interested to see if somebody got less than 366. How is your tree different from my tree here? So my tree, as you start adding weights to the graph, you start seeing that sometimes the most obvious answer isn't the best answer. So if you look at this part of the graph here, or this part of the minimum spanning tree, this vertex I'm pointing to here, I could have visited it by going from this vertex to this vertex, traversing paying a cost of 36, or from here to here paying a cost of 30. But if I wait a little bit until I reach here, I find that I can visit it at a cheaper cost by going from here to here and paying a cost of only 20. So these weights make the problem a little bit more interesting, and I'm interested to see if you got something less than 366. What would I need to do to change this tree to get something less than 366? Yes? This one? Anybody got anything less than 366? Yes? Does it matter if you use that 30 or that 30? So the question is, does it matter if you, if you use this 30 or this 30? There's two 30s here. Does it matter which one you use? And a more general way to answer this question is the minimum spanning tree unique? Can a graph have more than one minimum spanning tree? And the answer is a graph can indeed have more than one minimum spanning tree. So how do I know if one is better than the other? You add up the total cost and you see which one has a lower cost. So if both of them have the same cost, if both of them are 366, then both are equivalent. Both are equally good solutions. Both are equivalent solutions for the problem. And in computer science, sometimes you can prove that the problem has a unique solution. There's only one good optimal solution. Sometimes a problem can have more than one solution. So before we move on, did anybody get anything less than 366? Yes? Shh. So you got 334. So how is your minimum spanning tree different from this one? Which edge did I use which you didn't want, which you did not use? Whatever, yeah. Which of these blue edges here do you not have in your tree, and which do you have instead? What do you have instead of it?
Okay, so from start, I'm going to move so I used 31,
Mm-hmm.
and I used 25. And from 25, I went to 20,
Mm-hmm.
to 18,
Mm-hmm.
and then 20.
Mm-hmm.
I stopped there. I went back 1, and I used 26 and 41.
Mm-hmm.
41, I used 30 and 25.
Mm-hmm.
And then from 25, I used 30, 32. And then from 30, no, and then from 30, I went to 25, 20, and 15. So I did not use 28 right at the top.
Okay.
I don't think I mentioned those.
Okay. So did you visit this one here? The one at the bottom here.
Yeah, I visited that one through 31, and then I stopped there.
Okay.
Everything is the same now, except I used so the one where it's double it up to 30.
Mm-hmm.
Go up to the other end, go down to 30. That route.
Mm-hmm.
That route.
Okay, so use this one here instead. Okay. 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 So I'd have to check your solution, but I'm not claiming that this is necessarily the optimal. But the question then becomes, instead of eyeballing the graphs to know what's a good minimum spanning tree and what's not a good minimum spanning tree, what we need is an algorithm. What we need is a list of instructions that we can code as a computer program to enable a program to find the minimum spanning tree of a given graph. Okay? And I won't go into a minimum spanning tree algorithm because we're almost out of time, but this gives you a flavor. So it's not, what we aim for in computer science is not eyeballing problems to find solutions, but rather coming up with algorithms that automatically come up with the solution of the problem. Now, the last part of the activity is doing this in a distributed setting. Remember in the beginning of the talk I said that sometimes your problem size is just so large that you can't have one computer work on it. You have to have multiple computers working on it at the same time. And in that case, a question arises of how do you split up a problem among different computers? So in this case, you don't really have that large of a problem, but let's try to split it up among two people. So if you flip to the next 2 pages of your activity, you'll see that it's the same graph, but now we have 2 starting nodes. So it says start 1 and start 2. And I want you to find the partner next to you and try to split up the problem of finding a minimum spanning tree among both of you. So the minimum spanning tree will have to visit start 1, and it will also have to visit start 2. You have to visit all nodes in a minimum spanning tree. The question is, how do I do it in parallel? How can one person start from start 1 and another person start from start 2, and in the end, you get a minimum spanning tree? So talk among each other, and let's discuss this for 2-3 minutes. Maybe you can do the solution. Maybe you can actually find a minimum spanning tree with one person going from start 1, one person going from start 2, and then let's come back and see what you came up with. Okay, so can somebody tell me? Can somebody tell me how you split up the problem between yourself and your partner? So one of you starting from start 1, the other starting from start 2. How did you split up the problem between each other? So a simple solution would be, or any solution would involve one of the 2 partners taking some vertices and doing the spanning tree for them, the other partner taking the other vertices and doing the spanning tree for them. And you can either split the vertices in advance and say, okay, I'm responsible for this half of the graph, and you're responsible for this half of the graph. And then the question is, where do you split? And also, once you split, how do you connect the 2 halves together? So maybe I want to split along these edges here and give one person this half, the other person the other half. And then the question becomes, well, how do I connect the 2 halves? And how do I make sure I have the minimum cost connection for the 2 halves? Another possibility would be not to split the problem in advance, but say, let's both work on the problem from our respective beginning points, and we'll meet somewhere in the middle. Let's periodically check, have we met yet or not? And when we meet, let's reconcile our 2 graphs, our 2 spanning trees, and see if we can combine them to come up with an overall minimum spanning tree. So in general, when you talk about distributed algorithm, we're talking about multiple computers solving the same problem in parallel. An important question is how to split up the problem among the computers, and this is kind of an example of the issues we need to resolve when dealing with this question. Now, we'll stop here, but I have 2 more slides in your activity handout. The next slide is a different graph, and this is something for you to work on your own. Try to come up with the minimum spanning tree for this graph and see if it's going to be different than the other graph or the same. Not now, this is something to do later on your own. And then the last slide I wanted to show is a different kind of problem. So we talked a lot about this minimum spanning tree problem. And you can have, minimum spanning tree is not the only problem you can solve with a graph. So here is another interesting and very well-known graph problem, which is called the traveling salesman problem. And this problem goes as follows. So you have a graph where each node or where each vertex represents a store, and an edge between 2 stores means that an edge between 2 vertices means that there's a road connecting these 2 stores, and the length of the road or the distance you have to travel is the weight of the edge. And you have a salesman who needs to visit all of these stores in one day. He's going to start from one point, let's say store A, and then he's going to make a route through all of the stores and then come back to point A. And the question is, what's the shortest route this salesman can go through? If he needs to visit the same store twice, he will. And it doesn't have to be a tree. Actually, it can't be a tree because he's going to start from point A and come back all the way to point A. So the traveling salesman problem asks the question, what is the best path that a salesman can follow? We won't do it now, but I just wanted to leave it with you as an example of another kind of problem you can ask about graphs. So we'll wrap up here, and I hope you saw in this talk, first of all, a little bit more information about how Google gives us the search results when we type a query. And also I hope I gave you a flavor of the kinds of mathematics and algorithmic and engineering issues that are involved when you in the study of computer science. And I guess the next thing on the program is lunch. So thank you, and enjoy the rest of your day.